Welcome back. In this video, we are going to solve problem 5.58 that is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer Johnston, 6th edition. So statement is draw the shear and bending moment diagram for the beam and loading shown and determine the maximum normal stress due to bending. So you can see this is a simply supported beam AB having pin support at point A and a roller support at point B. And there is a uniformly distributed load from C to D having 80 kN per meter. At point A, we have counterclockwise movement of 60 kN, and at point B we have 12 kN into meter clockwise movement. And this is wide flange beam, which is W250 by 80. So you have to draw the shear and moment diagram. So let's start with the solution. So first step, if you remove this pin support at point A, so you will be having a vertical reaction force which is represented as A, and if you remove this roller support at point B, you will have a vertical reaction force B. So first we will find this A and B by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point B is equal to 0 and taking the counterclockwise moment as positive. So about point B, the first moment is 12 kN, which is clockwise, so I will take it as negative, so minus 12. The second moment is due to this distributed load, and this distributed load when converted into point load, so it will be equal to 80 multiplied by 1.6, and it will act at a distance of half of 1.6. which will be equal to 1.6 divided by 2 is 0.8. So 0.8 meter. So this load 80 into 1.6 into perpendicular distance is now 2 meter, and this is producing counterclockwise movement, so it will be positive. So I will write plus 80 into 1.6 multiplied by 2 meter, and the third load which is producing movement is A, and perpendicular distance is, this is 1.6, 1.2, 1.2 is 2.4, 3 and 4. It will be 4. So 4 into perpendicular distance is 4 meter, and this is clockwise, so it will be negative. So I will write it minus A multiplied by 4. And the last moment is 60 kN into meter, which is counterclockwise, so I will write plus 60. And their sum must be equal to 0. So minus 12 plus 80 multiplied by 1.6 multiplied by 2 is 256 minus 4 times A plus 60 is equal to 0. So I will take minus 12 plus 256 plus 60 will give you 304, and that will be 4A will be equal to 304. And from here A will be equal to 304 divided by, answer divided by 4 will give you 76. So 76 kN. Now you have this force. So what we will do is that we will calculate this B by using another equation of equilibrium, is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So A, which is upward, so 76 minus this 80 multiplied by 1.6. So 80 multiplied by 1.6 will give you 128 kN. So this is minus 128 plus this B is equal to 0. So from here you will get this 76 minus 128 will give you minus 49. Oh, sorry, 128, not minus 52. So B will be equal to plus 52 kN. Okay, now we have these two reaction forces. So what we will do is that we will move toward shear force and bending moment diagram. So for that I have to draw the vertical lines from the end of this beam. Okay, and first we will draw the shear force. So for shear force I will need a horizontal line to show the length x in meter, and on y-axis you have shear force having unit kN. Okay, so starting from A, I will write shear force. So starting from A, as you can see at point A, we have A force vertical reaction which is 76. So we can write it as VA is equal to 76 kN. Now from region A to C, you can see there is no load between these two, so it will remain same. So V shear force will be equal to 76 kN. Okay, at region of D, okay, from C to D and at point D, this shear force VD will be equal to, it will be equal to here at this point, the shear force will be equal to VA plus this one. You can see this 80 multiplied by 1.6 will give you shear force at this point. Clear? So I can write it, it will be equal to 76 minus 80 multiplied by 1.6. Okay, and that will give you 76 minus 128. So it will give you minus 52 kN. Okay, so VD is equal to minus 52 kN. Okay, from D to B, and you can see from D to B there is no load, so shear force at point from D to B will be equal to minus 52 kilonewton. Now you have all these values. So let's move and draw the shear force diagram. So for that I will take the scale. So let we take 1 division is equal to 25 kilonewton. So it is 50 and this will be 75. And same is the case minus 25 and minus 50. Okay. First at point A we have shear force of 76 kilonewton. So it will be somewhere here. So let this is 76. Now moving from A to C, this is your point C. Here, so from A to C you can see the shear force remains same. So it will be like, sorry, it will be horizontal. Okay, now what is the shear force at point D? So it is minus 52. So D point is this point. I can write D is minus 52. So it will be like this. Okay, minus 52 kilonewton. Now you can see that shear, the distributed load is a horizontal line with 0 degree. So shear force will be 1 degree higher and it will be a straight line by joining these 2 points, and slope will be decreasing because this force load is downward. Now from D to B there is same shear force which is minus 52 kilonewton, and at the last you can see you have B which is plus 52, and that will bring it to the 0. So this will be your shear force diagram. Again you can see that at this point you can see the shear force is 0, and at this point you will see in a while that bending moment will be maximum. So what we will do is that we will find the location of this point from this end. For that I will take let this distance, and the distance, this distance is taken as x. So this is x. So distance from this point till this point D, this will be equal to how much? So we will see that the total distance is 1.6. This is x. So this will be equal to 1.6 minus x. Now what we will do is that you can see you have two similar triangles. One is this one and another one is this one. So the ratio of their side must be equal to 0. So I will take x divided by 76. That will be equal to 52 divided by 1.6 minus x. So let me write it. X divided by 76 is equal to 1.6 minus x divided by 52. So from here 52x is equal to 1.6 times 76 minus 76x. So 52x plus 76x is equal to 121.6. 1.6 multiplied by 76 is 121.6, and 52 plus 76 is 128. So this will be 128x is equal to 121.6. So x will be equal to 121.6 divided by 128. This is 128. So you will get x will be equal to 121.6 divided by 128. So it will be 0.95. So x is 0.95. And that will be from this till this. So 1.2 plus 0.9 will give you 2.1. So this is 2 at a distance of 2.1 from point A. The shear force will be 0 at that point. 0.95. This is 95 meter. Now we will move toward the bending moment diagram, and for bending moment diagram we know that for bending moment, let me write it. Bending moment can be obtained by taking the area under the shear force diagram. So area of shear diagram. Okay. So first area you can see from A to C. So this is your point A, and this is your point C. So this is the first area under the shear force diagram, and this is rectangle here. So its area will be 76 multiplied by this length. So this length is 1.2 meter. So I can write it from A to C. The shear force will be, the area under the shear force, which is represented as integral of V into dx, that will be equal to 76 multiplied by 1.2, and that will give you 91.2 kilonewton. You can calculate it as well into meter. Now from C to A, first we will calculate this area from C to E, and let this point is E where shear force is equal to 0. So from C to E, this is the area under the shear force diagram, and you can see this is a triangle. So its area will be 1 over 2. This height, which is 76, multiplied by this x, which is equal to 0.92. This is the value 95. This is the value of x. So integral of V into dx will give you bending moment, and that will be equal to 1 over 2, 76 multiplied by 0.95. And that will give you the value equal to 36.1 kilonewton into meter. Now from E to D. So this area you can see E to D. So this is the, E to D area under the shear force is this one. And again, this is triangle. So its area will be 1 over 2 multiplied by 52 minus 52 multiplied by this length. And this length will be 1.6 minus 0.92. Okay. So I will write integral of V into dx will be equal to 1 over 2 minus 52 multiplied by, if you take 1.6 minus 0.95, that is 0.65. I will write 0.65. So multiplying this, we will get minus 16.9 kilonewton into meter. And the last area is from D to B. At the end, we have point B. So D to B is this portion. So area under the shear force diagram is rectangle. So you can see this will be minus 52 multiplied by its length is 1.2. So I will write it from D to B. Area under the shear force diagram is minus 52 multiplied by 1.2, and that is equal to minus 62.4 kilonewton. Now what we will do is that we will draw the bending moment diagram. So for bending moment diagram, again, if I extend these lines, so I will draw a horizontal line to show the length in meter, x in meter. On y-axis you have moment having unit kilonewton into meter. So you can see at point A we have been given bending moment MA, which is 60 kilonewton counterclockwise. So while drawing, remember that while drawing counterclockwise movement on bending moment diagram, it will cause it to go downward. So we will take each division as, for example, 30. So this is minus 20, minus 40, and minus 60. Each division is 20. So your first point will be this one. So this is bending moment at point A. Now what will be, I will write it MA is equal to minus 60 kilonewton into meter. Now this is your point C. This is your point C, this is your point E, and this is your point D. Okay. So what we will do is that moment at point C, MC will be equal to MA plus area under the shear force diagram from A to C. So I will write minus 60 plus 91.2 will give you moment at point C, which is 31.2 kilonewton into meter. So we will locate it. This is minus 20 plus 20. This is plus 40. This is plus 60. So 30 will be somewhere, 32 will be somewhere, 31.2 will be somewhere here, 31.2. Okay. And you can see that the shear force is a horizontal line with 0 degree curve. So bending moment will be 1 degree higher, and it will be a straight line, and slope will be increasing. Okay. So this was moment at point C. Now moment at point E is equal to moment at point C, which is 31.2 plus area under the shear force diagram for C to E, which is 36.1, and both of this will give you 67.3 kilonewton into meter. So at point E, this will be 67.3. So let's say 67.3 will be somewhere here. I will take it approximately 67.3 kilonewton. And you can see that shear force is a 1 degree line and slope is decreasing. So bending moment will be a 2nd degree curve. It will be like this and in clockwise direction. Okay. Now bending moment at point D will be equal to bending moment at point E. Why at point E? Because you can see at point E, this is the bending moment. So at point D will be equal to 67. I will cut it instead of that. I will write 67.3 plus area under the shear force diagram from E to D is minus 16.9 kilonewton, and that will give you 50.4 kilonewton into meter. So at point D, it is 50.4. So let's say 50.4 will be somewhere here at this point, 50.4. Again, you can see that shear force is a single degree, 1 degree line, straight line, and slope is decreasing. So bending moment will be 1 degree higher, and it will be a like curve in this form. Okay. And the last area, our moment at point B is equal to moment at point D, which is 50.4, and area under the shear force diagram from D to B, which is minus 62.4 kilonewton. That will give you minus 12 kilonewton into meter. So it will bring it to minus 12. So minus 12 will be somewhere here at this point. You can see this minus 12 will be somewhere here. This is minus 12 kilonewton into meter. And shear force is a horizontal line with 0 degree, and this area is negative. So bending moment will be 1 degree higher, and it will be a straight line, and slope will be decreasing. But at the end, you can see you have a bending moment of 12 kilonewton, moment of 12 kilonewton into meter, that is clockwise. So while drawing a clockwise moment on bending moment diagram, it will go upward. So minus 12 plus 12 will bring it to 0. So this will be your bending moment diagram. Now in second part, we have been asked determine the maximum normal stress due to bending. So again, we can say that maximum bending stress is equal to maximum bending moment absolute value divided by section modulus. So what is the maximum bending moment? So maximum bending moment from the bending moment diagram, you can see this is 67.3 kilonewton into meter. Okay, there is a meter sign as well. And that will be equal to 67.3 into 10 to the power 3 Newton into meter. What about section modulus? So Sx can be obtained from the appendix of this book. I will move toward the appendix. So you can see at appendix C, property of rolled steel. So you have to move SI unit W. What was given? W 250 multiplied by 80. So W250 multiplied by 80 will be somewhere downward. Okay, now you can see on this page. First, you have to be very careful. You have to see, sorry, W250 by 80. So W250 is this and 80 is this. So in that you will go to 983. So 983, but you have to go upward. And this is 10 to the power 3 cubic millimeter. So I will write it 983 into 10 to the power 3 cubic millimeter. Let me check it again. 10 to the power 3. Okay, yes. So in meter, it will be equal to 983 into 10 to the power 3, and it will be 10 to the power minus 12 cubic meter. And that will be, so the 10 to 10, 339. This is not 12, this is minus 9. Okay. So 983 into 10 to the power minus 6 cubic meter will be Sx. Now you have both the value, just plug it, 67.3 into 10 to the power 3 Newton into meter divided by 983 into 10 to the power minus 6 cubic meter will give you maximum bending stress. And this maximum bending stress will be equal to 68.5 into 10 to the power 6 Pascal, because Newton per meter square is Pascal. And from that, if you want to get it in megapascal, so it will be 68.5 megapascal, and which is the answer of our second part. So this was all about this problem 5.58. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also, give me your valuable feedback by commenting on my videos so that I may know how my videos are going on. Thank you. Welcome back. In this video, we are going to solve problem 5.54 that is taken from chapter number 5, Analysis and Design of Beam for Bending, and book name is Mechanics of Material by Beer Johnston, 6th edition. So statement is draw the shear and bending moment diagram for the beam and loading shown and determine the maximum normal stress due to bending. So you can see this is overhanging beam AB having uniformly distributed load from A to C, and its magnitude is 2 kips per feet, and at point B we have a point load of 6 kips, and this is wide flange beam which is W88 into 31. The total length of the beam is 14 feet, so you have to determine the shear force and bending moment diagram. So let's start with the solution. What will be the first step is that if you remove this pin support at point A, so you will be having a vertical reaction force which is A, and if you remove this roller support at point D, so you will be having a vertical reaction force which is D. So we'll find this A and D by using equation of equilibrium. So first equation of equilibrium that we will use here is sum of all moment about point D is equal to 0 and taking the counterclockwise moment as positive. So first force that is producing moment about this point D is this force which is A, and perpendicular distance is 12, and this is producing clockwise movement, so it will be negative. So I will write minus 12 times A. The second moment is produced due to this distributed load, and this distributed load when converted into point load, so it will be 2 multiplied by 6, and that will be equal to 12 kips, and it will act at a distance of 3 from C to midpoint or from A to midpoint. So this is 3 feet. So from this midpoint till this D, this will be 9 feet, and this is producing counterclockwise movement, so it will be positive. So I can write it plus 12 into 9. The last movement that is produced due to this force 6 kip, and the perpendicular distance is 2 feet, and this is producing clockwise movement, so it will be negative. So I can write it minus 6 times 2 is equal to 0. So from here we will get 12A plus 12 into 9 is 108 minus 12 is equal to 0. So 108 minus 12 will give you 96. So 12A plus 96. Okay, this is minus 12. Minus 12 plus 96 is equal to 0. So it means that A is equal to 96 divided by 12. And when you calculate it, so 96 divided by 12 will give you 8 kips. So 8, the vertical reaction force at A is 8 kip. Now we will find the second force D by using another equation of equilibrium. So that equation is, you can take sum of all moment about point D is equal to 0, or you can also take sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So A, which is 8, is upward, minus this 12 kilonewton that is downward, plus D minus 6 is equal to 0. So 8 minus 12 is minus 4, and minus 6 is minus 10. So D is equal to 10 kips. Now you have both these forces. So what we will do is that we will find the shear force and bending moment diagram. But for that, I have to draw the vertical lines from the end of this beam. So I will take the vertical line from the end of beam, and then there will be a horizontal line which will show you the length in feet, x in feet. Okay. On y-axis, you will be having V shear force having unit kips. Okay. What we will do is that for shear force, you can see at point A we have only A, which is 8 kips. So I can write it that VA is equal to 8 kips. 8 kips. Now what will be shear force at point C? So this will be your point C, this will be your point C, and this will be your point D. Okay. So at point C, V shear will be equal to VA, which is actually 8, VA, which is 8, plus this force 12 kips, because 6 into 2 into 6 will give you minus 12. So 8 minus 12 will give you minus 4 kip. Now from C to D, you can see you do not have any other force between C to D. So VC will be V to C, C to D, shear force will remain minus 4 kips. And from last D to B, V will be equal to VA plus VC plus VD, and that will be equal to minus 4, because this is minus 4 plus this 10, and VD is 10, and that will give you 6 kips. You can draw the shear force without this, but I have drawn it for your understanding. So let's plot this shear force diagram. For that, what we will do is that let's take each division is equal to 2.2 feet. 2 kips. So 2, 4, 6, and 8. Similarly, minus 2, minus 4, minus 6, and so on. At first point, we will have VA, which is how much? Which is 8 kip. You can see this is 8 kip. So your shear force start at this point. This is 8 kip. At point C, we have shear force minus 4 kip. So shear force at this point is this one, minus 8. And again, you can see that shear force, the load from A to C is distributed load, is a flat line with 0 degree. So bending moment will be 1 degree higher. And since this is downward negative, so we can join these two lines by using first degree line or straight line, and slope will be decreasing. Now from C to D, the shear force remains same, minus 4 kips. So from C to D, it will remain same. Sorry, this is not minus 8, this is minus 4. Okay. And at D, we have 6 kips load. So at D, it is 6 kip. So this is 6 kip. So shear force will change from minus 4 to 6. And from D to B, there is no other force. So it will remain horizontal. And at the end, you can see at B, we have minus 6, which will bring it to 0. So this is your shear force diagram. Now we will draw the bending moment diagram. So for bending moment diagram, again, I have to draw a horizontal line to show X, and that will be in feet. On y-axis, you will having moment there, that is having unit kips into feet. Okay. What we will do, as we know that area under shear force diagram gives you bending moment. Clear? So we will take the each area under the shear force diagram, and we will find the bending moment. So from A to E, you can see this is your point A, this was your C, and this is your D point, and this is your B point. Now at this point where this interact, like this point is E point. So we will take the first area is under the shear force diagram is from A to E is this area, and you can see this is a triangle. So its height is 8 and base is not known. Okay, so I will tell you that it will be how much we do not know about this. Since we do not know this distance, so what we will do is that we will calculate it first. So let I take this distance from this point till this point. Let me take this distance is equal to small e. So this distance from this till this point, this will be equal to how much? You can see that from this to this is 6 feet, and this is e. So remaining this distance will be equal to 6 minus e. So I will write it as this distance is 6 minus e. Now you can see you have two right angles triangles. So one is this one is this one, and another one is this one, and the ratio of their side will be equal. So I will take E divided by, if I take E divided by 8, let me show you, E divided by 8, that will be equal to 6 minus E divided by 4. So 6 minus E divided by 4. So you can calculate it. 4E will be equal to 48 minus 8E. So 4E plus 8E is equal to 48. So 12E is equal to 48. So E will be equal to 4 feet. 4 feet. So it means that this distance is equal to 4 feet. So remaining this E minus E will be equal to 2 feet because E is 4. So 6 minus 4 is 2 feet. Now we can draw the area under the shear force diagram to get the bending moment. So what I will do is that we know that area under AE is this one here, and this area I can write it that area under the shear force diagram is equal, since it is a rectangle triangle, so 1/2, base is 4 and height is 8. So that will give you 16 kip into feet. Now from E to C, you can see from E to C, the area under the shear force diagram is this area, and this is also a triangle. So height is -4 and base is 2 feet. So again, I will write is integral of V into dx will give you area. So 1/2 -4 into 2, and that will give you -4 kips into feet. From C to D, you can see this is the from C to D area under the shear force diagram is this area. So this height is -4, and from C to D distance is 6 feet. So I will write it integral of V into dx will give you area that will be equal to -4 times 6, and that is -24 kips into feet. And from last D to B. So from D to B, you can see this is D to B. The area under the shear force diagram is this area. So this height is 6 and this width is 2 feet. So I will write integral of V into dx is equal to 6 into 2, which is equal to plus 12 kips into feet. Okay, now we'll move toward the bending moment. And you can see that at start, the bending moment will be 0 at this point. So bending, because x is equal to 0, so MA is equal to 0. At point E, the bending moment will be equal to bending moment at point A, which is 0, plus area under the bending moment diagram, which is 16 from A to E. So it will be 16 kip into feet. At point C, moment will be equal to ME. ME is 16 plus the area from E to C, which is -4, and that will give you plus 12 kips into feet. At point at point D, you have moment will be equal to MC, which is net moment at till point C, and that is 12 feet, and moment about from C to D is -24. So that will give you -12 kips into feet. And at point E, you can see you have moment will be equal to MD, which is -12, plus moment from D to B is +12, which will give you 0 kips into feet at point E. Now we'll plot all these points to get the bending moment diagram. So for that, what I will take is that let each division is equal to 5. So 10 kips per feet, 10 kip into feet, 15. Similarly, -5, -10, and -15. Okay, at point A, the moment is 0. And at point E, this is your point E. At this moment is 16 kips. So it will be like this. This will be the point. What will be point at point C? Moment is +12. So this is your point C, and this will be your +12. It will be somewhere here. Okay. At point D, D is this point. You can see this is D point, this is C, this is E. So at point D, the moment is -12. So it will be somewhere here. This is your -12. And at point B, E. Sorry, this is your point B, not E. It will be 0. Okay. So 16, this is 12. Now, how we'll join these 2 points that will be defined by the shear force. Now, you can see shear force is 1 degree line and slope is decreasing. So, bending moment will be a curve and it will be in clockwise direction. So, we will get this curve. And same is the case, the shear force is a horizontal, 1 degree line with slope is decreasing. So, you will have to join these 2 points in clockwise direction. So, bending moment will be like this. Now, from C to D, the shear force is a horizontal line with 0 degrees. So, bending moment will be 1 degree higher and this area is negative there. So, what we will do is that we will join these 2 lines by using straight line or 1 degree line. Okay. And the last shear force is this one, which is also horizontal line with 0 degree, and this area is positive. So, bending moment will be 1 degree higher. It will be a straight line and slope will be increasing. So, this will be your bending moment diagram. So, we have drawn and we have covered the first part to draw the shear force and bending moment diagram. Now, in second part, we will move toward determine the maximum normal stress due to bending. So, we know that in part B, maximum normal stress due to bending. As we know that maximum normal stress due to bending is equal to maximum bending moment mod divided by section modulus, and we have been given that this is W8 by 31 wide flange steel. So from the bending moment diagram, you can see the maximum value of bending moment is 16 kips into feet. So I will write it maximum bending moment is equal to 16 kip into feet. So we will convert this into inch. So 16 multiplied by 12 kips into inch, because 1 feet is equal to 12 inch. So 16 multiplied by 12 will give you 192. So maximum bending moment is equal to 192 kips into inch. Now what about section modulus? For section modulus, we have to go to the book and we will go at the end where we have properties of roll steels appendices C. So in appendices C, you have to go to check W8 by 31. Okay, so here you can see this is W8 and this is 31. So in this line, you have to go and you have to search. This is SX, section modulus, so 27.5 cubic inch. So SX is equal to 27.5 cubic inch. Now you have both the values, just plug it in this formula. 192 kips into inch divided by 27.5 cubic inch. So that will give you 192 divided by 27.5 will give you 6.98. So maximum bending stress is equal to 6.98 kip per inch square. And that is also known as kips per square inch is equal to 6.98 KSI, which is the answer of our second part, and that is the maximum bending stress generated due to the bending. And that was all about this problem 5.54. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.